Critical points. We will find critical numbers using derivatives. Critical numbers are x values where the graph changes. So the first one is the relative maximum, sometimes called local maximum. So if you look at your slope to the left of the relative max, it is positive, and then at the relative max, it becomes 0, and then to the right of it, the slope becomes negative. So there's a change in the graph right there. The relative min, or the local min, same idea, is that before the relative min, the slope is negative. At it, it will be 0, and then to the right of it, it's going to increase to positive. So that's your relative minimum. And then the other one is the point of inflection. And the point of inflection is when the concavity changes. So it goes from concave down, which you can see there, kind of like a parabola opening down, concave down to concave up. And so where that change occurs is called the inflection point, or the point of inflection. Those will be the three types of critical numbers or points that we will be finding. To find the relative extrema, or max and min, just like I talked about, we want to find where the slope of the tangent is equal to 0. Okay? So just as I was talking about on the last slide, is that the slope will be 0 at that point, that tangent line. So what do? Well, we want to find the first derivative. So if we find the first derivative of the function, remember that has to do with the slope of the tangent line, we will then set it equal to 0. Okay, why are we setting it equal to 0? Well, because that's where the slope is equal to, that's where the slope will be equal to 0 of a horizontal line. So we're going to set it equal to 0, and then we will find the coordinates of the extrema once we know what those x values are after we solve. Okay. The second part that we're going to be looking at is the points of inflection. Okay, so the points of inflection, we're actually going to be finding the second derivative, which we haven't done yet, but it's just the derivative of the derivative. Okay, and we'll do the same thing. We'll set it equal to 0, and we'll solve, and we'll find the point of inflection on that. So let's go ahead and just take a look at an example here. We got to find the critical points. F of x is equal to 3x cubed minus 8x squared minus 4. So if we're looking for those critical points, we want to start with the first derivative. So we will find f prime of x using our derivative rules. 3 times 3 is 9. 3 minus 1 is 2, so 9x squared. 2 times 18 is 36. 2 minus 1 is 1. And then the constant minus 4 just becomes plus 0. All right. So that's the first derivative. So the first derivative, if I wanted to know the slope at any point on that graph, I would just plug it into the derivative. But we know what we want the slope to be. We want the slope of the tangent line to equal 0. So therefore, we're actually going to set the derivative, usually what we're finding, the slope, but now we know what we want the slope to be, so we're going to set the derivative equal to 0. And now it's a quadratic, so we're going to solve. We could actually divide both sides by that common factor of 9, so that'll leave us with x squared minus 4x is equal to 0. Factor out the GCF. And now we've broken up the quadratic into two linear terms, so set those equal to 0. And we get two x values, 0 and 4. So now we want to find the critical points. We want to find what they are. And so now we can plug those back into the function. We don't want to plug them back into the derivative. If we plug it back into the derivative, we should get a slope of 0. We already know that. So now we want to plug it back into the function. This will give us the y-coordinate of the point. So we'll plug them back into the function, and when we plug 0 back in, it looks like we will get negative 4. So one of our points will be at 0, negative 4, and then we will plug in 4, and we will get the y value when x is 4. And so if you plug that in, you will get a y value of negative 100. So we also have a point at 4, negative 100. So those are both critical points. We'll talk later on how to identify whether it's a max or a min. One of the ways on this one, because you know what a cubic looks like, and because its slope is, or that 3 is positive, it's going to be going in this direction. So you could actually identify the max and min just by knowing what the graph looks like. But we'll talk later about how we identify that, especially with graphs that are not as that are a little bit more complex than this one. So these right now are our critical points. Now we have one more thing to look at, and that is the point of inflection. So now we have to find the second derivative. So we're going to find the derivative of the derivative, which would give us, so we're finding the derivative of this one. That's the first derivative. So that'd be 9 times 2 is 18. So that's 18x to the first. And then the derivative of 36x is 36. So 18x minus 36. We've gone from a cubic to a quadratic to linear. Okay? Every derivative is going to lose a degree. So now we have linear. So now we're going to solve for a linear equation. We'll set it equal to 0 just like we did with the first derivative. Add 36, divide by 18. We get x equals 2. We want to find the actual critical point though, so we're going to plug 2 into the function. So we will get 3 times 2 cubed minus 18 times 2 squared minus 4, and if you plug that in, you will get a value of negative 52. So the other point that we have will be at 2 comma negative 52. So these are our critical points. And as I said, we'll identify max, min, relative max, relative min, and point of inflection a little bit later. Well, we know this one is a point of inflection because it's the second derivative, but the other two we'll have to identify later. Here's another example very similar to the first one I gave you. So right now I really want you just to pause your video and I want you to go through that process on your own and see if you can find, it is an x cubed again, so be looking for those 3 critical points. Alright, and there you go. So once again, finding the first derivative, setting it equal to 0, finding the x values for that, which we're at x equals 0 and x equals 2, plug in 0 back into the original function, not the derivative, the function. We're looking for the y values. So we found those 2 critical points, then we found the second derivative. Once again, found x equals 1, plugged it back in to get 3, and that would be our point of inflection. Alright, I want you to do this one more time, and I know it seems kind of silly, this would be the third example, but something different happens here. So I want you to go ahead and once again I'm going to pause the video, I'm going to work through the first part of it, and then we're going to kind of compare and see what happens as well. So go ahead, do the same thing you did on examples 1 and 2. So I want to start it back up after I found the first derivative and I found only a single point. This is still a cubic, and so we still have the shape of a cubic, usually looking something like that. But if it looks like that, we should have a relative max and a relative min. And right now I'm only getting, I have 2 factors, they happen to be the same, but I'm only getting 1 point. So what else can happen with a cubic? How else can a cubic graph look besides your kind of traditional one that I have on here? Well, let's go ahead and now look at the point of inflection. So we're going to find the second derivative. So that'll give us 12x plus 12 plus 0. So then we can set it equal to 0. We could divide both sides by 0, or not by 0, by 12 if we wanted to, or we could just factor or subtract 12, I guess is what we should do. Subtract 12. Divide by 12, so x is equal to negative 1. And you might notice that we have already found x equals negative 1. It was negative 2. So we're getting the same exact point on the second derivative. So is it a point of inflection? Is it a max, a min? What's going on? Well, here's the thing. If you graph this on your calculator, the original function, it will look something like this, where you don't have a max and a min, a relative max and min. All you do is have a change in concavity. So where it's going from concave down to concave up, that will be your point of inflection. It's not a max or min. So we actually only have one critical number, and it happens to be a point of inflection. So if this happens where you do the first derivative and then your second derivative gives you the same point, then it's because it's a point of inflection. Your slope is still 0 at that point, but it's a changing concavity instead. All right, and the last thing I want to talk about is to determine if a critical number is a maximum point, a minimum point, or a point of inflection. So we're going to use the values of x slightly smaller and larger than the given x, okay? And we're going to do this in the derivative because this is going to talk about the slope of that point before and after. And if it's a relative max, as we had talked about, it'll be positive to the left and then negative to the right. And I'll show you that again. So what you see down below here is if the derivative of x to the left, that's at negative, is greater than 0, and if the derivative of x to the right is less than 0, then it's a maximum. And so let's think about that. All right, if it's just to the left of the point, the slope is greater than 0, so it'd be going up like that. So just to the left, your slope would be positive, and then there's your point, whatever it might be, and then just to the right, it will be less than 0, which is negative. So if it's going from positive to negative, then that would represent a maximum. If just to the left is less than 0, and just to the right is greater than 0, well, now it's going negative first, and then to the right of the point is greater than 0, it's positive, then that would be a relative minimum. For the point of inflection, you will look at the second derivative, just like you do when you're finding the point of inflection. You'll look to the left and to the right of the second derivative, and if the signs are different, then it will be a point of inflection. We don't care necessarily about what they are, but if they are different, then we're going to have a point of inflection. So if we want to find out specifically about whether a point is a max, min, relative max or min, or a point of inflection, we have to check the slope just to the left and just to the right of those points. And that's what we're going to do right now on example 4. So we're going to determine if the points 1, negative 4, 0, negative 2 are critical numbers, and if they are, what type are they going to be? So we're going to start with the first derivative. The first derivative, 3x squared minus 3. And so what we're going to do at x equals 1, right here, we're going to plug in to the derivative a point just to the left of 1. So we'll do 0.9. So you'll plug this into the derivative, and you can use your graphing calculators to help you identify this. But when we plug in 0.9 into the derivative, we get negative 0.57. And now we want to plug in a value just to the right of 1 into the derivative. This is the slope at x equals 0.9, right before 1. This will be the slope, and this is 0.63. So this is the slope at x equals 1.1. So it has gone from a negative slope to a positive slope. So what is the point 1, comma, negative 4? It will then be a relative minimum. And so once again, the point 1, comma, negative 4 would be a relative minimum because the slope goes down and then up, negative to the left, positive to the right. So go ahead and try the point 0, comma, negative 2. See if you can figure out what that point is. Is it a critical number, and if so, or a critical point, and if so, what type? So I found the derivative again, same thing. Plugged in a point just to the left and just to the right of x equals 0 into the derivative. It tells me the slopes are both the same. So now we need to go to the second derivative, which would be 6x, and I guess that's it. So now we're going to plug in those same x values just to the left and just to the right of 0 and see what the second derivative is. Because the first derivative, the signs didn't change, so now we have to go to the second derivative. So now when I plugged in negative 0.1, I got negative 0.6. And when I plugged in 0.1 into the second derivative, I got 0.6. So there's a sign change right there, and that's what it says. If we have different signs, then it's a point of inflection. So we know that the point 0, negative 2 is a critical point, and specifically it will be a point of inflection. So that's how you can determine whether a point is a critical point or a critical number, by looking at the slopes of the first derivative, and if that doesn't work, then looking at the values of the second derivative when you plug a number just to the left and just to the right, just to the left and just to the right of that point that you're looking for, the x value. So in summary, what are you looking for? You're looking for your critical points, your relative max and mins, and your point of inflection. We do have a first derivative. We also learned about the second derivative helping us find the point of inflection.